Hello all and welcome once again to my YouTube channel Engineering Physics by Sanjeev. We are starting a new MCQ series. Through this series we will discuss MCQ questions on various topics. Hope this series will help you in the preparation of different competitive exams like MHTCET, JEE Main, NEET, etc. If you like this session, please subscribe to the channel and share with your friends. So let us start with the session. In this session we will be discussing some MCQ questions on quantum mechanics and we will focus on the topic de-Broglie hypothesis. So this is question number 1. Which of the following statements about the energy in a quantum is true? 4 options are given. Option A, varies directly with frequency. Option B, same for all frequencies. Option C, varies inversely with the frequency, and option D, none of the above. So here, according to Planck's relation, a quantum of energy is given by E is equal to h nu, where h is called as Planck's constant and its value is 6.63 into 10 raised to minus 34 joule second. So from this relation we can say energy in a quantum varies directly with frequency. So for this question number 1, option A is the correct option. The energy in a quantum varies directly with frequency. Next question. The matter wave associated with a particle of mass m and moving with velocity v has a wavelength. 4 options are given again. Lambda is equal to h upon mv, lambda is equal to h square upon mv, lambda is equal to mv upon h, and lambda is equal to h upon mv square. We know the de-Broglie hypothesis states that there is a wave associated with every moving particle moving with velocity v, and wavelength of this wave is given by lambda is equal to h upon p, where h is Planck's constant and p is momentum of the particle. So p can be written as the product of mass and velocity, and therefore in this problem option A, lambda is equal to h upon mv, is the correct option. So the wavelength of the wave associated with a particle of mass m and moving with velocity v has a wavelength lambda is equal to h upon mv. Let us move on to the next one. Which one of the following is the correct statement? The statements are: only subatomic particles in motion are accompanied by matter waves. Next statement is: any particle in motion, whether charged or uncharged, is accompanied by matter waves. Next statement is: no particle, whether at rest or in motion, is ever accompanied by matter waves. And last statement is: only charged particles in the motion are accompanied by matter waves. So which one of these 4 statements is the correct statement? That is the question. So here the answer lies in the de-Broglie hypothesis. De-Broglie hypothesis states that there is a wave associated with every moving particle moving with velocity v, and the wavelength of this wave is given by lambda is equal to h upon p. So according to de-Broglie hypothesis, wave is associated with every moving particle, whether it is charged or uncharged. So here option B is the correct option. Any particle in motion, whether charged or uncharged, is accompanied by the matter waves. Question number 4. The wavelength of the wave associated with an electron accelerated by a potential difference of v volts is, 4 options are given again. A is h upon 2 MeV, B is h upon square root of 2 MeV, C is h square upon 2 MeV, and option D is h upon square root of 2 pi MeV. So which one of these 4 options is the correct one? So to find the answer of this problem, let us do simple calculation. The kinetic energy of the electron is given by 1 by 2 mv square. Let us multiply and divide by m. So we get m square v square upon 2m as the kinetic energy, which can be written as p square upon 2m, and therefore momentum can be written as square root of 2me. Now for this electron which is accelerated by a potential difference of v volts, we can write this kinetic energy also to be equal to E into V, where E is charge on the electron and V is the potential difference which is used to accelerate the electron. And therefore the momentum becomes square root of 2mev. Now according to de-Broglie hypothesis, we can write the wavelength of the wave associated with electron as h upon p. So this h upon p can be written as h upon square root of 2me, and we have shown that this p is equal to square root of 2mev, and therefore lambda becomes h upon square root of 2mev. So in this case option B is the correct option. So the wavelength of wave associated with an electron accelerated by a potential difference of v volts is given by h upon square root of 2mev. Question number 5. Electron behaves like a wave as it can be deflected by an electric field, or can be deflected by a magnetic field, or it can ionize gas, or it can be diffracted by a crystal. So which option is the correct option here? Diffraction is the phenomenon which can be explained by considering the wave nature only. In order to confirm the behavior of electron as a wave, Davisson and Germer did one experiment. In that experiment, they made the electron beam to be incident on a nickel crystal which is used as a diffraction grating, and they obtained the diffraction pattern. As the diffraction pattern occurs only if waves are present, Davisson and Germer confirmed the existence of wave associated with the electron. Therefore, the answer to this question is electron behaves like a wave as it can be diffracted by a crystal. Question number 6. To verify de-Broglie hypothesis, Davisson Germer experiment used the phenomenon called interference, polarization, or electron diffraction, or tunneling of electrons. So which phenomenon was used by Davisson and Germer in their experiment to confirm the existence of wave associated with the electron? We discussed this in the last question also. Davisson Germer did one experiment to confirm the existence of wave associated with the particle, and in that experiment what they did, they made the electron beam incident on nickel crystal and obtained the diffraction pattern. Now the diffraction pattern cannot be explained by using particle nature of an electron. To explain this diffraction pattern, we can consider only the wave nature, and this confirms the existence of wave associated with the electron. Further, Davisson and Germer calculated the wavelength using de-Broglie hypothesis, and they calculated the wavelength using Bragg's law of diffraction also, and they found that the wavelength calculated using de-Broglie hypothesis matches with the wavelength calculated using Bragg's law of diffraction, and this confirms the de-Broglie hypothesis. So this is how Davisson Germer performed an experiment based on electron diffraction to verify the de-Broglie hypothesis. So for this question number 6, option C, electron diffraction, is the correct option. Okay, select the correct option here. Matter waves are, the options are transverse mechanical waves, electromagnetic waves, longitudinal mechanical waves, neither electromagnetic nor mechanical waves. So which one option is the correct option? If we consider electromagnetic waves, These waves have electric and magnetic fields associated with them. Matter waves do not have such electric and magnetic fields associated. Mechanical waves need medium for the propagation, but matter waves can propagate in vacuum also. So matter wave is not a physical entity or quantity. It is not an oscillation of the particle or anything like that. Matter wave is associated with any moving particle and can propagate in vacuum also. So answer to this question is matter waves are neither electromagnetic nor mechanical waves. Next question. De-Broglie waves are associated with, options are moving neutral particles only, moving charged particles only, all moving particles, all particles whether in motion or at rest. So to answer this question, let us consider de-Broglie hypothesis. De-Broglie hypothesis states that there is a wave associated with every moving particle moving with velocity v, and wavelength of this wave is given by lambda is equal to h upon p. So de-Broglie is saying wave is associated with every moving particle. So the particle may be neutral, may be charged, there will be wave associated. And it is saying wave is associated with every moving particle. So the particle at rest do not have a wave associated with it. So answer to this question is de-Broglie waves are associated with all moving particles. Let us move on to the next question. The proton and alpha particle are accelerated through the same potential difference. The ratio of their de-Broglie wavelengths is, options given are 1 by root 2, root 2, 2 root 2 and 2. So let us find out which is the correct option. Alpha particle is made up of 2 protons and 2 neutrons. So mass of the alpha particle is equal to approximately 4 times the mass of proton. If we write mass of proton as m, mass of alpha particle will be equal to 4 into m. Because of 2 protons, charge on alpha particle is equal to 2 into E. We can write charge on proton to be equal to E. So with this we can write the ratio of wavelengths as lambda proton, that is wavelength of proton, upon lambda alpha particle, that is wavelength of alpha particle, to be equal to. Now this lambda proton according to de-Broglie hypothesis can be written as h upon square root of 2 MeV. Using the same relation, we can write the wavelength associated with alpha particle as h upon square root of 2 into 4m into 2eV. Here 4m is the mass of alpha particle and 2e is charge on the alpha particle. Let us do simple calculation. Here h will get cancelled, 2 will get cancelled, m will get cancelled, e will get cancelled, v will get cancelled. And we will be left with square root of 4 into 2, that is square root of 8. Square root of 8 can be written as 2 root 2. And therefore, the ratio of de-Broglie wavelengths associated with proton and alpha particle comes out to be 2 root 2. So 2 root 2 is the correct answer for this question. Let us move on to the next question. Which one of the following will have the largest de-Broglie wavelength if moving with same speed? So electron, alpha particle, proton and oxygen atom, all of them are moving with same speed, and we are asked to find out which particle will have largest de-Broglie wavelength associated with it. We can answer this question with the help of de-Broglie hypothesis. According to de-Broglie hypothesis, the wavelength of the wave associated with a moving particle is given by lambda is equal to h upon p, where p is momentum, and therefore we can write lambda is equal to h upon mv. So from this relation we can see wavelength of the wave is inversely proportional to the mass. Now whatever the particles given, in these particles mass of the electron is smallest, and as the mass of electron will be smallest, the de Broglie wavelength associated with the electron will be largest. So because the wavelength is inversely proportional to mass, the particle with smallest mass will have largest wavelength. So answer to this question is electron. Next one, an electron and a proton are accelerated through the same potential. If their masses are me and mp respectively, then the ratio of their de Broglie wavelengths is, the options are 1 mp upon me, me upon mp, and square root of mp upon me. Again, to find the ratio here, we will use de Broglie relation. Wavelength associated with the electron is given by h upon square root of 2 me ev, where me is mass of the electron, e is charge on the electron, v is the potential difference through which the electron is accelerated. Wavelength associated with the proton will be given by h upon square root of 2 mpev, where mp is mass of the proton, e is charge on the proton, which is equal to charge on the electron. V is potential through which the proton is accelerated. So here it is given that the potential used to accelerate the electron and proton is same. So this EV will get cancelled, 2 will get cancelled, and the ratio of wavelengths associated with electron to the wavelength associated with proton will come out to be square root of mp upon me. So mp upon me is the option D. So option D is the correct option here. Next one, all these are the questions based on de Broglie relation. The de Broglie wavelength of a particle of mass m moving with kinetic energy E is given by, options are square root of h upon 2me, h upon square root of 2me, square root of h upon 2me, and h upon 2me. So which is the correct option here? According to de Broglie relation, the wavelength of the wave associated with a particle of mass m and moving with velocity v is given by lambda is equal to h upon p, where p is momentum of the particle, which is given by product of mass and velocity. We can write this p in terms of energy by using this simple calculation. Kinetic energy of a particle is given by 1 by 2 mv square, where m is mass of the particle and v is velocity with which the particle is moving. Let us multiply and divide by m. We can write it as m square v square upon 2m. That is nothing but p square upon 2m, because this m square v square can be written as p square. And from this we can write p is equal to square root of 2me, and therefore the de Broglie wavelength lambda, which is given by h upon p, so in this relation p can be replaced by square root of 2me, and therefore lambda can be written as h upon square root of 2me. So let us find this option. Here h upon square root of 2me is given in the option B. So option B is the correct option here. The de Broglie wavelength of a particle of mass m moving with kinetic energy E is given by h upon square root of 2me. Question number 13. An electron accelerated by a potential difference V has a de Broglie wavelength lambda associated with it. If the electron is accelerated by a potential difference of 4V, then its de Broglie wavelength will be, the options given are 4 lambda, 2 lambda, lambda by 2 and lambda by 4. We know that the wavelength of the wave associated with an electron accelerated by a potential difference of V is given by lambda is equal to h upon square root of 2 MeV. Now if we accelerate the same electron by a potential difference of 4V, then the de Broglie wavelength will be h upon square root of 2 Me into 4V, which can be written as 1 upon square root of 4 into h upon square root of 2 MeV. This h upon square root of 2 MeV is nothing but lambda, and square root of 4 is 2, and therefore the wavelength associated with the electron which is accelerated by potential difference of 4V is lambda by 2. So C is the correct answer here. Question number 14. A material particle is in thermal equilibrium at temperature T. The wavelength of the de Broglie wave associated with it is, the options are h upon 2 kT, option B is h upon square root of 8 pi square mkt, third option is h upon square root of 3 mkt, and the fourth option is h upon square root of 4 pi square mkt. To find the correct option here, let us consider at temperature T, the kinetic energy of the particle 1 by 2 mv square is equal to 3 by 2 kT, thermal energy here. 2 will get cancelled. Let us multiply both sides by m. So we can write m square v square is equal to 3 mkt. And m square v square is nothing but p square. So p is equal to square root of 3 mkt, and we can write de Broglie wavelength as lambda is equal to h upon p, that is equal to h upon square root of 3 mkt. So the wavelength of de Broglie wave associated with the particle which is in thermal equilibrium at temperature T is given by h upon square root of 3 mkt. Next question. The crystal used in Davisson Germer experiment as a target material was, the options are silver, nickel, copper, none of this. Davisson Germer performed an experiment to confirm the existence of wave associated with the electron, and in this experiment they tried to get the diffraction pattern with the help of electron beam. To get diffraction pattern, they made electron beam to be incident on a nickel crystal. So they use nickel crystal as a diffraction grating in their experiment. So correct answer here is option B. The crystal used in Davisson Germer experiment as a target material was nickel crystal. Question number 16. Which of the following graphs represents the variation of particle momentum and associated de Broglie wavelength? So 4 options are given. Which is the correct option? We can find the nature of the graph by using de Broglie relation. Lambda is equal to h upon p. So we can write p is equal to h upon lambda. Here h is Planck's constant, and therefore the graph of p versus lambda will be of the type y is equal to 1 by x graph, and this graph is represented in option number C. So option number C is the correct option. This graph is for y is equal to 1 by x. Question number 17, a small numerical. A particle with mass of 10 raised to minus 31 kg is moving with a speed of 10 raised to 5 meter per second. The de-Broglie wavelength of the particle is, the options are 6.63 into 10 raised to minus 8 meter, 66.3 angstroms, 6.63 angstroms and 6.63 into 10 raised to minus 7 meter. So in order to solve this, we will have to do a little calculation. So here is a simple solution. Lambda is equal to h upon p according to de-Broglie relation. P is equal to mv, the product of mass and velocity. So lambda is equal to h upon mv. The value of h is 6.63 into 10 raised to minus 34 joule second. Mass is given as 10 raised to minus 31 kg and velocity is given as 10 raised to 5 meter per second. So we can simply calculate this as 6.63 into 10 raised to minus 34 plus 31 minus 5, which comes out to be 6.63 into 10 raised to minus 8 meters. So correct option is option A. 6.63 into 10 raised to minus 8 meter will be the de-Broglie wavelength of the particle. Next one, the ratio of de-Broglie wavelengths of proton and an alpha particle will be 1:2 if their options are kinetic energies are in the ratio of 1:8, velocities are in the ratio of 1:8, kinetic energies are in the ratio of 8:1 and velocities are in the ratio of 8:1. So which is the correct option? Ratio of de-Broglie wavelengths of proton and alpha particle should be 1:2. To solve this, we will need this relation. Mass of the alpha particle is equal to 4 times mass of proton. It is given that ratio of de-Broglie wavelengths of proton to de-Broglie wavelength of alpha particle is 1:2, that is 1/2. So we can write lambda p upon lambda alpha equal to 1/2. Lambda p is h upon mp vp and lambda alpha is h upon m alpha v alpha. We can write it as h upon mp vp into m alpha v alpha upon h. M alpha can be written as 4 mp and this ratio is given to be 1/2. So here we can cancel mp with mp and this 4 can be taken on other side and we can write v alpha upon vp is equal to 1/8 and therefore vp is to v alpha is equal to 8:1. So the ratio of velocities of proton and alpha particle comes out to be 8:1 and this is given in option number D. So option number D is the correct option. Ratio of velocity of proton to alpha particle, velocity of alpha particle, that is 8:1. Let us check for kinetic energies. For kinetic energies, we can write the de-Broglie relation using the kinetic energy. So wavelength of the wave associated with proton is h upon square root of 2 mp-ep in this case. mp is mass of the proton and ep is kinetic energy of proton, and de-Broglie wavelength of the wave associated with alpha particle is h upon square root of 2 m alpha e alpha, where m alpha is mass of alpha particle and e alpha is energy of the alpha particle. So again this can be written as h upon square root of 2 mp-ep into square root of 2 m alpha e alpha upon h. M alpha can be replaced by 4 into mp And if you calculate this, MP will get cancelled, 2 will get cancelled, and we will get the ratio as square root of 4 E alpha upon EP equal to 1 by 2. So this ratio is already given as 1 by 2, and therefore take square E alpha upon EP will be equal to 1 upon 4 into 1 upon 4. So we are taking square, so this 2 will become 4 here, 2 square, and this 4 comes on the other side. So E alpha upon EP is 1 upon 16, and therefore the ratio of energies, kinetic energies of proton and alpha particle, it comes out to be EP is to E alpha as 16 is to 1, but this 16 is to 1 is not given in any of the option for kinetic energy, and therefore there is only one answer in this problem. The ratio of de-Broglie wavelengths of proton and alpha particle, if it is 1 by 2, then the ratio of velocities, ratio of their velocities must be 8 is to 1. This one is a simple numerical. The wavelength of de-Broglie wave associated with an electron accelerated through 150 volt is, the options are 1 angstroms, 15 angstroms, 20 angstroms, 0.1 angstroms. So here to find the answer, we will have to do simple calculation. According to de-Broglie hypothesis, lambda is equal to h upon p, that is equal to h upon square root of 2 me, and this energy E can be written as E into V, because the electron is accelerated using potential difference of V volts. Here V is equal to 150. So let us substitute the values of all the constants and voltage V, potential V. H is 6.63 into 10 raised to minus 34 joule second. M is 9.1 into 10 raised to minus 31 kg. E is 1.6 into 10 raised to minus 19 coulomb. V is given as 150 volts. So if you do the calculation, this calculation turns out to be 1 into 10 raised to minus 10 meters, that is 1 angstroms. So the wavelength of de-Broglie wave associated with an electron accelerated through 150 volts comes out to be 1 angstroms. You can check this calculation. Again a simple numerical. An electron moving with a velocity 6.6 into 10 raised to 5 meter per second, its de-Broglie wavelength is, the options are 1.1 into 10 raised to minus 9 meters, 1 into 10 raised to minus 5 meters, 1 into 10 raised to minus 10 meters, and 1 into 10 raised to minus 7 meters. So again we will need to do simple calculation here. So according to de-Broglie hypothesis, lambda is equal to h upon p, that is h upon mv. H is 6.63 into 10 raised to minus 34 joule second. M is 9.1 into 10 raised to minus 31 kg for an electron. V is given as 6.6 into 10 raised to 5 meter per second. So if you calculate this, it will turn out to be 1.1 into 10 raised to minus 9 meters. So option A is the correct option. You can check the calculation. Now this one is the last one. The wavelength of de-Broglie wave associated with a moving particle is independent of its. The options are mass, charge, velocity, momentum. The simple one can be answered using de-Broglie relation. So according to de-Broglie relation, lambda is equal to h upon p, that is equal to h upon mv. So clearly the wavelength depends on mass, wavelength depends on v, velocity, and product of mass and velocity is momentum. So the wavelength depends on momentum also. So here the option remaining is charge. So the wavelength does not depend on charge, it depends on mass, velocity, mass and velocity, and therefore momentum also. So we are at the end of this session of MCQ questions on de-Broglie hypothesis. I hope this session was helpful to you. If you like this session, then please subscribe to the channel and share this session with your friends also. Thank you.